Welcome to qnawire.
This is problem number 63 of the Stewart Calculus 8th edition, section 2.8. Recall that a function f is called even if f of negative x is equal to f of x for all x in its domain, and odd if f of negative x is equal to negative f of x for all such x. Prove each of the following. Part A, the derivative of an even function is an odd function. Part B, the derivative of an odd function is an even function. So what we're going to do is we're going to start with part A. We're going to use our definition of a derivative, and we're going to assume whatever is given to us and then try to prove exactly that assumption. So for example, the first part, part A, the derivative of an even function. So we're going to start with an even function where f of x, where the function has a property of when we plug in negative x, we still get the same function out. So the derivative of this even function is an odd function. So if the derivative is an odd function, then it has to have the property that when you plug in a value, such as negative a, an odd function should have this equal to the derivative of at that value, the opposite of that, so negative there. So this is what we're trying to prove. Okay. Um, so we will use our definition here. Limit as x approaches a of the function f of x minus f of a, or we're plugging in negative a, so I should clarify, since our input is negative a, we are approaching negative a here, and we're approaching negative a here in the function, and then over here we're doing x minus negative a. Okay, the next step, we want to use the property of the function. The function in part A is that the function is even. That's the assumption. So if the function is even, when we plug in a negative number, we get the same function as if we were to have plugged in a positive number. So this will be the same as f of a here. But in the denominator, we'll have x plus a. Okay, here we're going to have to make a substitution. We're going to let u equal negative x. So this is just a substitution, changing the variable from x to u. So if u is negative x, x is negative u. Okay, and this allows us to flip the sign of a here in the limit. So here's exactly what we will see. The limit is u. We changed that from x to u, meaning that negative a flips in sign since u was negative x. So we went from x to negative u, and then negative u flipped to positive u. That means negative a flips to positive a. And then we have x is negative u, so the function appears the function evaluated at negative u minus f of a, and then in the denominator we have negative or x, which is negative u plus a. Great. Our next step is to again recall that our function is even. If our function is even, when we input a negative number, it's the same as if we would have input a positive number. So f of negative u is the same as f of u minus f of a divided by, and then here what we should notice is that we can factor out a negative and call this u minus a in the denominator. And this is an important part here because this negative can be factored out of the limit. So what is remaining? We have remaining limit as u approaches a of f of u minus f of a over u minus a. If this looks familiar, it is. It is the definition of the derivative. So what we have concluded here is that this is exactly equal to negative, since the negative was factored out, negative f prime of a. And this is exactly the conclusion we're getting to, that because we assumed that a function was even to begin with, we did the derivative, and we plugged in a negative a, and what we ended up getting was the opposite of the derivative function evaluated at a, which is exactly the definition of an odd function. So we proved that the derivative of an even function is an odd function. In part B, we're going to do the same except switch the assumptions. We're going to assume that the original function f is odd, and then we're going to attempt to prove that that this derivative evaluated at negative a gives us the derivative f prime evaluated at positive a, because that's the property of an even function. Okay, so we're going to do this limit as x approaches a of this function, or we're approaching negative a. Correct this because we're plugging in negative a of this function f of x, which is an odd function. That's a new assumption in part B, minus f evaluated at negative a divided by x minus negative a. Okay, our next step, limit as x approaches negative a. Our function here, f of x, stays the same. But here, f of negative a, well, we're taking the derivative of an odd function. F is an odd function in part B. If f is odd, then f of negative x is the same as negative f of x. So f of negative a is the same as negative f of a. So this negative in the front changes to a positive. F of a, we no longer have the negative a in there. And the denominator is x plus a. So we use, at this point, the same substitution we had earlier. Same substitution where we let u equal to negative x and x equal to negative u. And this serves to switch the sign here of the negative a. So we get the limit as x approaches, or we substituted x with u, which flips the sign for the a. So we're now approaching positive a. U approaches positive a of f evaluated at x. Well, x we substituted with negative u. So that goes there. Plus f of a divided by x plus a. Okay. We still have to substitute this x here, because x we replaced with negative u. So this was the replacement step. We went from x here, here, and here to u, negative u here and here, and then the negative u here just served to switch the sign of the a. So it was negative u approaches a, negative a, now it's u approaches positive a. And then now we're going to use the property of the function u approaches a. So this function f, we are assuming in this part B that it is an odd function. If it's an odd function, then f of negative u will be equal to negative f of u plus f of a divided by negative u plus a. So here's the important step. Our next part will be to factor not just one negative 1 from the numerator, but also negative 1 from the denominator. In the numerator, we'll have negative 1 times f of u minus f of a, and in the denominator we'll have a negative 1 factored out, leaving u minus a in the denominator. So this negative here cancels out with this negative, and what we're left over with is the limit as u approaches a of the quantity f of u minus f of a over u minus a. And u can be any variable. It's a dummy variable. It could have been x. It's exactly the same as this definition of a derivative that we encountered initially, that we use initially. So if we replace the x, it doesn't matter. It just serves this entire quantity is exactly equal to the derivative of f evaluated at a. So what we did is we started with the derivative of f at negative a, and with the assumption that the function f is odd, we were able to conclude that the derivative function evaluated at positive a is the same as the derivative function evaluated at negative a, which is a property of even functions. So we have proven in part B now that the derivative of an odd function is an even function. And that concludes the proof for both parts A and B.